Hello students, in this lecture number 9 in Collegiate-Physics classes, we welcome you. In this lecture, we will show that the Newton's laws of motion are a special case of quantum mechanics. Newton's second law of motion can be proved that the wave function described by psi, which forms the wave packet, the average motion of wave packet can be explained as Newton's second law of motion. The principle of correspondence between motion of a wave packet and motion of a classical particle, both are identical. The law which governs the motion of a classical particle also governs the motion of a wave packet. As we know, the Newton's second law of motion, dr by dt is equal to p by m, where r is the position vector and p is the momentum vector. Similarly, dp by dt is equal to minus grade v, it is equal to force F, where p is linear momentum, v is potential energy, F is force. These two formulas are formulas of classical mechanics. We can say that it is Newton's second law of motion. These two formulas can also be derived from the motion of wave packets. And so we can say that Newton's second law of motion is a special case of classical mechanics. In this discussion, we will have Ehrenfest theorem. This theorem is regarding the behavior of wave packet as classical particle. The Ehrenfest theorem states that the average motion of a wave packet agrees with the motion of corresponding classical particle, and the formula for average motion of wave packet is same as that of the equation for the motion of classical particle. We will deduce this theorem. We know that the expectation value of x corresponding to position vector r, the position vector r has three components, x component, y component and z component. This x is the component of position vector r. Its average value or its expectation value in classical mechanics is written as integral minus infinity to plus infinity psi star x psi dx. This is the formula for expectation value of x. Now, the time derivative of this expectation value x dx by dt will be obtained from this equation. First of all, psi star and x will be kept constant, and the derivative of psi will be del psi by del t dx plus del psi star by del x psi dx. Now, we know the time dependent Schrodinger wave equation as this. This is the time dependent Schrodinger wave equation. From this equation, we have calculated the value of del psi by del t. Here, in equation 2, the value of del psi by del t will be substituted from this equation 3. Again, the complex conjugate of this Schrodinger equation will be written, and from that complex conjugate equation we will substitute the value of del psi star by del t in this equation. So, again, from the Schrodinger time dependent wave equation, we will write its complex conjugate form, and from this equation we find del psi star by del t is equal to this much. This is equation 4. Now, in equation 2, we substitute the value of del psi by del t and del psi star by del t from equation 3 and 4, and that equation is solved further. Then finally we draw this conclusion: dx by dt is equal to px by m. Here x is the x component of position vector r and px is the x component of momentum. Similarly, we can show that dy by dt is equal to py by m and dz by dt is equal to pz by m. In this way, the first part of the equation, vector d by dt of vector r is equal to p by m, will be proved. And the next part of this question will be discussed in the next lecture. The detailed calculation is given in the note which is at the last of this video. You can see that note, and if you find any difficulty, you can go to the comment box. I will solve that difficulty. And at present, we are taking a stop in this question. The rest part of the question will be discussed in next question. Thank you. Hello students, you are welcome in the lecture of second part of lecture number 9. The lecture number 9 is regarding Ehrenfest theorem. The Ehrenfest theorem consists of two parts. The first part has been already discussed. Now the second part. In the second part, we will show that rate of change of momentum is equal to Fx, force of x component, and this is also equal to minus del v by del x. This is the component of force, and here P is the component of momentum. So this equation can be derived by quantum mechanics. In quantum mechanics, as you know, each observable physical quantity is represented by a appropriate operator. P is the momentum, and its corresponding operator in quantum mechanics is minus I h cross del y del x. So we will calculate the expectation value of momentum. The expectation value of momentum of a wave packet may be written as d by dt of this expected value of p, and this will be equal to minus I h cross d by dt of integral minus infinity to plus infinity psi star del psi by del x dt. Here this d by dt of psi star del psi by del x will be differentiated by parts. First, psi star is kept constant and del psi by del x will be differentiated del by del t of del psi by del x, plus psi star will be differentiated and del psi by del x will be kept constant. So we get this equation number 1, d by dt of p is equal to this much. Here this del t and del x can be interchanged because psi is a function of x and t and it is perfect differential. So this can be written as del by del x of del psi by del t. Now we will take the help of Schrodinger time dependent wave equation. I h cross del psi by del t is equal to minus h cross square by 2m del 2 psi by del x square plus v psi, where the symbols are of usual significance. Or del psi by del t will be equal to 1 by I h cross under bracket minus h cross square by 2m del 2 psi by del x square plus v psi. This is obtained from Schrodinger time dependent wave equation. Now its complex conjugate form will be taken. Then it will become del psi star by del t is equal to minus 1 by I h cross under bracket minus h cross square by 2m del 2 psi star by del x square plus v psi star. Now in equation number 1, del psi by del t will be substituted from this equation number 2 and del psi star by del t will be substituted from equation number 3. I have told that this del by del t and del by del x can be interchanged because psi is a function of x and t and it is perfect differential. So putting the value of del psi by del t and del psi star by del t from these Schrodinger equations, we get this d by dt of p is equal to h cross square by 2m integral psi star del q psi by del x cube minus del psi by del x del 2 psi star by del x square under bracket dx minus integral psi star del by del x of v psi minus v psi star del psi by del x under bracket dx. This is equation number 4. In the next part of this question, we will show that in equation number 4, we will show that this term will be 0 and only this term will survive. See, d by dt of p is equal to h cross square by 2m integral minus infinity to plus infinity psi star del q psi by del x square plus del psi star by del x into del 2 psi by del x square minus del psi star by del x into del 2 psi by del x square minus del psi by del x into del 2 psi star by del x square dx. And this term will be equal to minus infinity to plus infinity psi star. This will be solved, differentiated by parts. So del v by del x into psi plus psi star v del psi by del x minus, this can be written as psi star v del psi by del x, the whole under bracket dx. Now see, this term is added and it is subtracted both. Then there will be no difference in the equation. So this equation number 4 will become equal to this much. Now d by dt of p will be equal to h cross squared by 2m integral minus infinity to plus infinity del by del x of psi star del 2 psi by del x square minus del psi by del x del psi star by del x dx. Minus this term will be cancelled. This term and this term will be cancelled. So it will be equal to minus integral minus infinity to plus infinity psi star del v by del x psi dx. Now the integration of this first part will be equal to psi star del 2 psi by del x square minus del psi by del x into del psi star by del x lower limit minus infinity plus upper limit plus infinity minus integral minus infinity to plus infinity psi star here minus del v by del x psi dx. See, this minus term is brought here and it becomes plus. Since the value of psi star at minus infinity and at plus infinity is 0. Similarly, del psi by del x is also 0 at minus infinity and plus infinity. This is the property of wave function psi because it is a well behaved function. So this term will become 0 and the last term will be equal to this term will be equal to expected value of minus del V by del x, where V is the potential energy. And we know that minus del V by del x, this term is equal to Fx, where F is the force and Fx is the x component. So this is in a component form, in one-dimensional form. In three-dimensional form it will be written as minus grade V is equal to F. And in this way, this is Newton's second law of motion and it has been deduced from the classical mechanics from wave packet formula, and this is called Ehrenfest theorem. And in this way the Ehrenfest theorem is completed. Thank you for attending the class. Thank you.